Today on How It's Made. Racing leathers. Evaporative cooling towers. Wood rocking chairs. And wire wheels. With no car frame around them, motorcycle racers look to their clothes for protection. One-piece suits called racing leathers provide it. They're made of padded leather, and the design is form-fitting and aerodynamic. Motorcycle racing leathers are a kind of body armor. Equipped with padding and airbags, the suit is a protective shell. It must fit the rider like a second skin. To achieve this, racing leathers are usually custom-made by a team of specialists. They take over 40 measurements as the racer assumes different poses. The pattern maker types the measurements into a computer. Special software creates a pattern for the suit. She assembles the pattern parts on the screen to ensure they match up and then sends the drawings to a printer. It prints the life-size patterns onto large sheets of thin tracing paper. A member of the team then sprays the backs of the paper patterns with adhesive. She presses the patterns onto sheets of cardboard. She cuts out the cardboard following the designs on the paper. The cardboard backing gives the patterns a more substantial structure. Before cutting the leather, they clamp a sample in an automated tool that moves it repeatedly across a piece of sandpaper. This confirms that the leather is strong enough to withstand significant abrasion. They apply graphics to the patterns to estimate the placement, and then they're ready to cut. The cutter carves into the white leather with a thin blade. He follows the lines of the pattern and leaves a generous margin. The parts will be cut more precisely later. He transfers the leather panels to a large sheet of paper stretched across the bed of a printing machine. Light glue applied to the paper keeps the leather pieces in place during printing. The printer's jets spray designs onto the parts. It uses inks that have been specially formulated for leather. The inks start to dry immediately, but they leave the printed leather to set overnight for a full cure. Next, using a hinged scissor frame, they stretch and expand an elastic fabric. A member of the team sprays adhesive onto the back of a leather panel. She presses a piece of Kevlar onto the leather, and this reinforces it. She then places the Kevlar and leather panel on the fabric that's still pulled tight in the scissor frame. She stitches the leather and Kevlar part to the stretched material, creating a ribbed pattern. She now cuts the panel to its final dimensions. The elastic fabric contracts, causing the leather to pucker into accordion-like folds. A seamstress stitches the rib panel to the back of the motorcycle racing suit. It takes over 200 parts to achieve the desired shape and fit. Some of them, like these shoulder protectors, are made of molded plastic and foam. They're designed to dissipate the force of an impact. Meanwhile, at a test station, they slam weights into a molded knee pad and measure the energy that penetrates. Now, a member of the team inserts a pair of pads into suit leg pockets and secures them with Velcro. The suit is ready for airbags. She installs them over the shoulders. She tucks the microprocessor and gas inflation canisters in the hump. This is an aerodynamic part at the back of the suit. She connects the sensors and powers up the airbags. LED lights on the sleeve illuminate, indicating that they're operational. With a leather suit complete, they sew a microfiber liner. The liner wicks sweat away from the body, making the suit cooler to wear. The racer suits up and tests the fit, and they make any final alterations. These racing leathers are now ready for the thrills and spills of the sport. Evaporative cooling towers keep large buildings and industrial machines cool. Circulating liquid carries the excess heat to the cooling tower, typically installed on the roof. The tower uses cold water to cool that fluid, then transfers the heat to the atmosphere through an evaporation process. Pumps move the fluid carrying the excess heat through the cooling tower's closed-circuit coil. Nozzles spray the coil with cold water. The spray water absorbs the heat, and the cooled fluid returns to the building. Fans blow air onto the now warmed spray water to evaporate just enough to release the heat. Then the cold water loops back to the spray system and the cycle repeats. Depending on the size, the coil is made up of as many as 56 circuits. A circuit is a zigzag tube, 1 inch in diameter. The mill forms a continuous straight tube from a strip of carbon steel. The rollers progressively curve the edges upward until they join at the top. The last station on the mill welds the joined edges together to form a continuous seam. Next, workers transfer the straight tube to a semi-automated tube bender, which forms it into a circuit. Depending on the size of the circuit, there can be as few as 6 bends or as many as 18. To make a circuit with 18 bends can require a straight tube that's over 300 feet long. Once all the circuits are ready, workers stack them on a frame. Then weld the tube ends to the corresponding holes of a steel plate. They close up the plate with a cover called a header. After clamping the header in position, they weld it in place, forming a pressure-tight seal. The coil is now fully constructed and ready for testing. Technicians submerge it in water, then pump air through at high pressure and look for bubbles, which would indicate a leak in a circuit. If they do find a leak, they either repair or replace the circuit. Meanwhile, work is underway on the cooling tower's mechanical section. A computer-guided laser cutter prepares the steel panels that make up the section's rugged structure. Workers then bend the panels where required with a machine called a press brake. Then they assemble the panels to build the structure. Meanwhile, another team has assembled the mechanical section ceiling, which houses the fans. Workers lower this onto the structure. Inside the mechanical section, they install the belt that links the motor's pulley to each fan pulley. After tightening the belt screw with an impact wrench, they test the fans. Meanwhile, the coil has been dipped in molten zinc to make it corrosion resistant. Workers mount it next to the cooling tower's mechanical section. They cover it with a steel housing and install the water spray system on top of it. The sprayed cold water absorbs the heat from the fluid circulating through the coil. The fans then cool the water by evaporation as it flows downward through a bundle of PVC sheets. The machine first heats the PVC to soften it, then stamps it with a mold plate. This imprints a proprietary pattern of peaks and valleys. This pattern is the secret to the evaporative cooling process because it moves the air and spreads the water in a way that maximizes efficiency. Workers stack the sheets on pole supports to construct a bundle of 300 sheets. After placing the bundle in a housing, they install it over a basin. This basin collects the cold water before it's pumped back up to the sprayers to repeat the cycle. This completes the cooling tower's lower module. They now mate it with the upper module, containing the fans, coil, and spray system. This evaporative cooling tower has more than 300 times the capacity of a typical residential air conditioning system. Now that's pretty cool. The rocking chair was invented back in the 18th century, when people first thought of putting skates or rockers on the bottom of chairs. The tilting movement it produces reminds us of a cradle or a rocking horse, which might be what makes rocking chairs so comforting. These stained jumbo rockers are caned in a herringbone pattern with Indonesian rattan vine. 22 pieces of solid Appalachian red oak form the frame and the base of these rocking chairs. To start, the carpenter connects the tenon joints of the stretchers to the mortises of the back frame and hammers them in place with a rubber mallet. A caner drains a coil of binder cane, which is soaked overnight to make it more pliable, while weaving the back and seat of the rocking chair. She uncoils the rattan vine threads and starts wrapping the back frame from bottom to top. The wrapping and weaving process for each chair lasts about 8 hours and requires about 2,000 feet of rattan vine threads. When the caner reaches the end of a rattan vine, she fastens a new coil to the first one. She staples the threads together and closes them tight with a pair of needle nose pliers. She continues wrapping the back frame. She tightens the wrapping around the frame, leaving no gap between the cane strands. She then tucks the final strand underneath one of the rails. She now starts the weaving process, moving from left to right, using the wrapping as a base grid for the pattern. Each thread passes over 3, then goes under 3. She turns the frame over to weave the back of the frame in the same fashion. The challenge is to keep the weaving straight and sleek to give it the classic herringbone finish. A carpenter attaches side stretchers to the front posts, which are already assembled to the front rounds. He hammers the pieces in with a rubber mallet and assembles the seat frame with the back posts. There's no need for glue. The seat caning will solidify the rocker structure. A caner uses the same rattan vine that was used on the back to wrap the seat frame. He makes sure there are no gaps between the strands of cane before he starts weaving the herringbone pattern. He weaves the over-under pattern in the center of the seat, where there's more slack in the wrapping. Then he pushes the threads up with a wooden wedge to tighten the caning as much as possible. Straps reinforce the structure of the chair before the seat frame is caned. To ensure authenticity, a carpenter brands the left armrest of each chair with the original branding iron used by the company since 1875. He hammers the armrest into the back post. Then he aligns the spokes of the front post with a hole in the armrest. A clamp keeps the back and front post aligned while he inserts the armrest. A wooden wedge in the spoke prevents the armrest from disconnecting from the front post over time. The carpenter hammers it in with the steel hammer. The wedge replaces the need for glue and ensures a snug fit between the armrest and the front post. The carpenter secures the armrest to the chair by drilling a solid brass carriage bolt through the back post. With a belt sander, he levels the wedge and front post with the armrest and makes it smooth to the touch. Before the runners or rockers are assembled to the base, the carpenter stains the chair. The oil-based stain protects the wood and brings out the natural grain of the solid oak frame. The stain is then sealed with 2 coats of clear varnish that will endure high humidity levels, sun, and climate changes. The carpenter assembles the runner to the base and measures the distance to the front post. This ensures an even rocking movement on every chair. He fastens them with brass carriage bolts. The finished chairs will endure the test of time and provide comfortable seating options for both indoors and outdoors. Wheels with wire spokes ruled the highways until the 1970s, when they were replaced by cast alloy ones. But factories still make wire wheels for the classic car market and for drivers who want to use them to customize their ride. Wire wheels suspend the weight of a car with flexible metal spokes arranged in a specific geometric pattern. They start with an aluminum alloy disc. A factory worker clamps the disc in a metal spinning machine. This machine shapes metal as if it were a piece of clay. It spins the disc at a high speed, while a series of tools press it to a round form. It takes 20 minutes to transform the flat disc into a wheel rim, complete with a bead for the tire. The process also causes the metal to undergo molecular transformation and to become stronger. After polishing, a worker moves the rim under a tool that punches dimples in it. The dimples will accommodate nuts that will be used to secure the spokes. He drills into the dimples to create holes for attaching the spokes. He angles the holes slightly so that the spokes sit correctly. He stamps the wheel's design number and other identifying information into the outer edge of the wheel rim. By now, the wheel's steel centerpiece has also taken shape. An employee turns it for even spacing as the tool repeatedly punctures it. This creates rows of small holes in both the inner ring and outer flange. He then drills those holes larger to prepare for the spokes to be assembled to the part. At the next station, a worker inserts spokes into a press that bends its ends with hooks. The angle of the hook varies depending on the part of the wheel the spoke is to be assembled to. He adjusts the settings on the press to achieve the different bends. Then it's over to an automatic blade that cuts the spokes to length. This also varies. They cut outer spokes longer and inner ones shorter. He now places the ends of the spokes in a device that rolls them against the cutting block. It carves threads in the metal in mere seconds. With the spokes now hooked, cut, and threaded, the wire wheel is ready for assembly. The employee hooks the appropriate spokes into the holes in the centerpiece. He places the aluminum rim around the centerpiece. He attaches the threaded ends of the spokes to the rim using steel nuts that fit into the tapered holes. He screws them loosely into place. He configures the spokes in a crisscross geometric pattern specified by the engineers. This pattern is designed for strength and flexibility, but it also gives the wheel a visual appeal. Once he's laced all the spokes from the centerpiece to the rim, he tightens the fittings. This secures the assembly, but it's not the final torque. They now transfer the loosely assembled wire wheel to a shaft and turn a crank to lower the centerpiece within the rim. This brings the spokes into the correct position, and a worker tightens them substantially, all 72 of them. He does the final tweaking by hand. 7 hours in the making, this wire wheel is now ready to roll. With the rubber tire attached, he secures the wheel to the car using a single large nut. It's called a knockoff nut because you simply knock it off to change the tire. It's just one of the things that makes the wire wheel a classic choice. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.